Hello, everybody, and welcome back. I hope you're all doing well. Root Beer here with question at number 4 on our 2010-2011 Alberta contest, part 2 of the contest specifically. Okay, so like our last 3 questions, this one's going to be written. What have we got? Determine all functions f from the set of integers to the set of positive integers so that... Oh, what an interesting property we got. F of n minus 1 plus f of n plus 1 is less than or equal to f of 2 times f of n for all integers n. Okay, so a couple quick thoughts. When you're doing function questions, and these don't come up a lot on younger year contests, think your grade 7, your grade 8 contests, you don't see a lot of function questions. But you might notice that sometimes they pop up on things like a Euclid contest, so grade 12. And a lot more advanced contests will have them in university, like the Putnam contest will have these, show that there's this set of functions, or Olympiad level papers. So, if you're really, really good at math, you will write like the Canadian Open paper, and then from there you might get invited to write, say, the Canadian Math Olympiad and things like that. And those are for really, 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 really good people. But you'll get these sorts of questions. Maybe you can get them all over the place, but you'll find that they become more common the higher up you go in terms of difficulty level. Okay? So you might start encountering them, as we're encountering this one here. And there's a couple things I'd like to pass on about function questions. One, it's very important that you look at whatever few properties you're being given and really focus on what they mean rather than just, oh, it's this plus this plus this. So I'm looking at this one, I notice, oh, 2 fn's. Fn is in the middle of n minus 1 and n plus 1. So it's almost like they're averaging a little bit. If you just rearrange, divide both sides by 2, you can see Fn has to be bigger than or equal to the average of its neighbors. Okay, so that's a way to actually describe what's going on rather than physically saying, or literally saying, f of this plus f of that must be less than or equal to. And if you have a real sense for what the property is trying to do, these questions, they're a little easier. Okay? Other things to think about, don't think of them as, functions that must be polynomials or must be this, that, or the other. Okay, they're just functions that are out there. And they're not anything in particular. They might not even be particular functions that you've even heard of. So don't be assuming, oh, this must be some sort of a polynomial that does this. No, there are other functions out there. Something else to focus on, usually I find, having done a lot of these sorts of questions, that if you see it, usually the first sort of function that pops into your head that works like that is usually either the only function or all the functions sort of look like that. So, for example, maybe I realize that the function f of x equals x plus 1 satisfies this. I don't think it does. But suppose I think that. Maybe that's the only one, or maybe it's everything that looks like ax plus 1, or maybe there are only lines and quadratic functions or any other sort of functions won't work. Okay? But usually, or maybe it's got to be a constant function or something like that. Okay? But usually that's sort of the only thing that there really aren't that many weird, sort of obscure, very technical to describe functions out there. Usually it's a very simple, very obvious function that when you are presented with it, when you say, oh, when somebody comes along and says, have you tried this function? You see, oh, it really obviously fits the definition. Usually those are sort of the only ones out there. Okay? And so sometimes that can help you narrow down your approach when you get this family of answers or possible functions. Then it becomes sort of the question of, okay, can I show that anything other than these won't work? Okay? So that's just some advice on these types of questions. Now I'm going to look silly if none of that helps me with this, but usually function questions like these all follow roughly the same sort of style. Okay, so as I say, want to focus on the property that we're being given. So as I said, experiment with this, maybe rewrite it a little bit. Okay. So fn has to be greater than the average of its two numbers. So that's something we could look at. Or something else we could do, we could leave the fn plus 1 here. Split the two fn's into fn plus fn. Bring the fn minus 1 over here, and now subtract another fn. So this is another way to rearrange it. And so if we're thinking about this, what does this expression say? So I know what this one says. Function is greater than the average of the two beside it. But what's this saying? Well, if you imagine sort of the functions on a little bit of a line, because it should be on the integer number line, and you got n minus 1 and n plus 1. The difference, the sort of the step up that you go from here has to be more than the step up you go. This is f of n. The heights are f of n. I'm pretending I graph. So we're sort of always leveling off. We're never sort of sharply increasing because the difference between the function is only ever less than or equal to the previous difference. Okay? So it's important to be able to sort of interpret what you're saying and try and run into problems, try and work things out like that. Okay. Now, as for functions that I look at this and I see immediately this should work, something like, well, I noticed that if f was just the identity function, whatever number you put in, you put out, that would satisfy it. So f of n minus 1 is just n minus 1, and f of n plus 1 is just n plus 1. And if you add those up, you get 2n, which is less than or equal to 2n, which would be f of n, 2f of n. Okay? Now, the reason that isn't going to work for me is because they said we're going from the integers to the positive integers, so I can't plug in -3 into my function and get -3 out. Okay, so is this going to cause a problem? The identity function really obviously would satisfy this. Can I think of something else that would really obviously satisfy this? If the function were constant. So for a second I thought 0. Certainly 0 plus 0 is less than or equal to 2 times 0 if everything's 0. But also that's true of 1. If everything were 1. Or if everything were 2. Okay? So there might be something else I'm missing, but my thought might be, okay, maybe only constant functions can work. Okay? So I think about that. Okay, if that were the case, if only constant functions will work, how could I use this property in my various rearrangements to show that's the case? Okay. That maybe there's something stronger, that it's not actually that it's less than or equal to 2fn, that it's actually has to be equal to 2fn. Is there going to be an issue there that I can sort of exploit? Okay. So if the function were constant, and we look at this way of writing it out, the second one that I've got here, if the function were constant, then this would be 0 and this would be 0, right? Because it's the same number, so 2 minus 2, 2 minus 2. So let's suppose for a second that it wasn't. Okay. So suppose fn isn't the same as fn plus fn minus 1 for at least one n. Okay? Suppose that's the case, or it doesn't really matter. Does it have to be fn and fn minus 1 or fn plus 1? Just suppose we've got a difference. Okay? What I want to do is show that this is impossible. Okay? And if I find it's difficult to show that, then I need to re-examine. Maybe there's something else I've missed. Maybe there's some other type of function other than constant ones that work. Okay? So suppose that's the case. Right? For example, so then fn plus 1 minus fn is not equal to 0. So let's suppose it's some value k. Now, just because my function f spits out numbers that are positive doesn't mean that, this one spits out 2 and this one spits out 13. I could have my difference be negative. Now, the difference could be any integer. So we're going to have to sort of exploit that. But what do we know? Well, if k is positive, so let's break it up into cases. If k is positive, then I know k is fn plus 1 minus fn, but that's less than or equal to the difference in the previous ones, okay? Which is less than or equal to the difference in the ones before that. Right? So, I think what we can do is we can show that working backwards. So if I rearrange this, so rearranging fn plus k is fn plus 1. And, actually, let's say less than or equal. And so fn minus 1 plus k, so rearranging this expression here, is less than or equal to fn. Okay? So I can always see, so since k is positive, I can say, all right, then f of n minus 1 is, actually, it's got to be less than, right? Well, no. So here's what I'm going to say. So then, since k is positive, we see that fn minus 1 must be less than fn, and fn minus 2 must be less than fn minus 1. And so fn minus 3 must be less than fn minus 2, and so on. And we get this nice little chain. Now, why would something like this matter? Okay? Why am I going at this particular approach? Well, we know that our outputs, so the f-ofs, have to be in the natural numbers, so the positive integers, right? Okay? But the positive integers have, they sort of bottom out. They have a lowest value. The integers don't, but the positive integers do. So what we get here is this nice little descending chain. So we have a descending chain. Everyone is less than the one before it. I don't know, the ith one. Okay. Now, where can we go from there? So we just keep getting a descending chain. We can keep going further and further back. The integers, the inputs, we can keep making them less and less. So we could say something like, if f of n is m, then we see f of n minus 1 can't be equal to m. It's got to be less than it. So it's less than or equal to m minus 1. And f of n minus 2 is less than or equal to m minus 2. It could be a lot less, but we know that it can't be bigger than that. It can't be bigger than this because f of n can't be bigger than this. And it has to at least be 1 less than f of n minus 1. Right? And so on. So f of n minus I must be less than or equal to m minus I. Now, why does this matter? Well, suppose I took away, because m is, just a positive number. So this one here would have to be less than or equal to m minus m plus 1, be less than or equal to negative 1. But our function only outputs positive integers. So this is impossible. Or what we sometimes say is we've reached a contradiction. Okay? Now we only made one assumption. We said, what if k was positive? What if the difference between these two that are different is positive? And as soon as we do that, we can make this nice little chain that keeps getting smaller and smaller, smaller values, but we know there's a smallest value to the natural numbers, but there isn't a smallest value to the integers, so we can keep going back and back and back. So that works if k is positive. Now I think the same thing should work if k is negative, but we're going to make our integers bigger and bigger and bigger and bigger, okay, and show the same sort of problem. Okay? And we might have to slightly adjust things, but this approach may work. In which case, well, what have we got? Well, our big assumption was, suppose that for some n, fn and fn plus 1 were different. If we can show that that always leads to nonsense, you know, if you get a difference that's positive or a difference that's negative, you always get nonsense there, then that must also not be true. So another proof by contradiction. Okay? And so then the opposite must be true. So for every value, for every n, fn must be the same as fn plus 1, and that's what a constant function is. All the values are the same. And as we already noted, we can see the constant functions definitely satisfy the condition. Okay? So instead, suppose k is less than 0. Okay? So now what we're going to do is we're going to say, okay, k is, I think this would be the right approach, k is fn plus 1 minus fn, but now that's bigger than the difference of the next two. Is bigger than or equal to the difference of the next two after that. And so on. Right? But this thing is definitely less than 0, so these ones will not be able to be equal. Okay? And then, well, what can we say? So fn plus 1 is fn plus k, and fn plus 2 is going to be less than or equal, so just ignore this part, bring this over to this side. This difference must be less than or equal to k, so fn plus 2 must be less than or equal to fn plus 1 plus k. Okay? But since k is negative, it's like we're subtracting, so fn is less than or equal to something smaller than fn plus 1. And so now I'm getting a smaller and smaller chain again. But I can always, add 3 to n. I can always make a bigger integer to plug into my function. But the outputs are getting smaller and smaller as we go along. Well, this can't happen. So again, we might say, call f of n plus 1. So we used capital M, let's use capital L. So then f of n plus 1 must be less than or equal to L minus 1. fn plus 3 has got to be less than this value. So at most it's L minus 2. And that's only if fn plus 2 actually is L minus 2. Okay? And we might say in general, f of n plus I would have to be less than or equal to what? It looks like for 3 we go to 2, for 2 we go to 1. So it looks like it'll be L minus I minus 1. Okay. So we know that's got to be true, but then, so L, by the way, is a positive integer. So then f of n plus L plus 2, just to be on the safe side, must be less than or equal to L minus L plus 2 minus 1, which is minus 1 again. So once again, we get an impossible outcome. F of something equals a negative integer. Okay? So our initial assumption that there was some n, so that fn plus 1 was not the same as fn, must be false. Because no matter what this difference is, if it's positive, we have a problem. If it's negative, we have a problem. So it's got to be 0. So fn equals fn plus 1 for all n, or f is constant. Okay? So all we've managed to show so far is if a function satisfies these properties, it must be constant. We haven't finished the question, because now we need to take the admittedly short, quick explanation and say, oh, by the way, all the constant functions do work. Okay? So we got to finish the question, though. We have to finish that up. And it's important to remember, just because you show the function has to have the properties you want, doesn't mean all the functions with those properties work. Okay? So we now show all such constant functions work. So I might say let a be a positive value because the outputs are positive. Let fn be a for all n. Okay. Then f of n minus 1 plus f of n plus 1 is a plus a, which is 2a, which is less than or equal to 2a, which of course is equal to 2 times f of n. So as a conclusion, what phrasing did they use? Determine all functions that work like this. So the only functions with the property are those functions which are constant. And there we go. Okay, nicely done. Okay, so I'd like to draw your attention to the things that I mentioned off the top of my head. I don't know if we used all of them, but we definitely took a look at the property and said, can I think of a stupid, simple, very basic function that works like this? The constants, and that gave us a little bit of direction. We definitely played around with the property a little bit. Okay? And there were I don't think I mentioned this at the start, but there are two sort of sides to these sorts of questions. You got to show that every function has exactly these properties and that every function with these properties will work. So as soon as you have an idea of what functions will work, tell them, explain to them why those functions do always satisfy the property, and then show that only functions that satisfy those properties must be those. Okay, so two sides of what you got to do here. But that's it for question number 4. Up next, question number 5, and that'll finish off our 2011 paper. I hope to see you there. Okay, until then, take care and have a wonderful day.